Suresh, for inviting me to this workshop. So this is my first time in this workshop. So thank you. And so today I'm going to talk about counting black holes as algebraic varieties. And this is a work which is essentially the paper counting n equal to 8 black holes as algebraic varieties, which I wrote with my PhD student, Saurav Maji. So before I begin, let me start with the outline of what I'm planning to cover. So I will give a brief sort of big picture of why this microstate counting business is important for black holes, and then also in the context of string theory. And then we'll directly move on to this intersecting d-brane system that we have, and Lagrangians and the fields on this system, and the supersymmetric ground states of this system, which basically will connect with microstates of the black hole. And the main essential point is to count the number of supersymmetric ground states. So here it turns out that in this kind of systems, because we have switched on some background moduli fields, the number of supersymmetric ground state will come as points. So you can actually count them. And then we'll use some computational algebraic geometry techniques to see how to basically efficiently count large number of equations, polynomial equations in a large number of variables. So these variables here will be the expectation value of various fields that are there for this intersecting d-brane system. And then the supersymmetric ground state are basically like the F term, D term vanishing of a Susi quantum mechanics. And that basically gives you a lot of polynomial equations. So the whole talk is about how to efficiently compute it. And we'll talk about two main kind of strategies. One is this Hilbert series, which is a exact strategy. And I will like to spend more time here because, first of all, it is exact, and it is also more widely applicable in the sense that it goes beyond zero-dimensional varieties or collection of points that I am going to talk about here. It also works for other finite dimensional varieties. And then I will go to some numerical techniques, which are almost exact in the sense that they are numerical, but they are very efficient and really precise. And I will just talk about maybe the first two, homotopy continuation and the monodromy, and Newton polytope. We'll see if we have time, we'll go. And then I will maybe end with the outlook. So nowadays, the theme for the last 3 decades probably is that we as physicists are getting more interested in these Riemann surfaces, and mathematicians are looking into the Feynman graphs, but this is what it is. So in this context, let me begin by basically saying what are the relevant references here. So the first 2 papers are the ones that I wrote during the end of my PhD with Ashok and Shapnamay and Richard. And they basically deal with the various nitty-gritties of how to basically build this pure d-brane system. So how to construct the Lagrangians and so on and so forth. So I will not spend too much time doing that. Of course, I will say something about it. And then I'll quickly move on to the actual computation of these polynomials and their solutions, for which the later part of the references, there is a good book by Cox, which basically sets up the stage for this field of computational algebraic geometry, but none of the techniques are that I'm going to use are mentioned here. The techniques are fairly recent as 2022 in math literature. So, and these techniques are there. They basically developed the mathematics for it, and parallelly, well, with a sort of a delayed phase, sort of algorithms are also got developed. So I'll be mostly for the exact Hilbert series computation, I will be mostly using Singular or Macaulay, and for the numerical ones, this homotopy continuation is a very good package now written in Julia to do this homotopy continuation in a very reliable and efficient way. So this is completely parallelizable. So if I scale my computational system, things will scale. So let me start with the overview. So I do not have to tell this audience about black holes and the importance of counting microstates for the black holes. But anyway, the black holes have a black hole area, which is basically connected to the black hole entropy. And then there are, of course, corrections to it. So the main question here is what is the statistical interpretation of a large black hole entropy that we see or we calculate. Then this cannot be answered just from the classical GR point of view, that because of various uniqueness theorems, if you basically fix masses and charges, so you have to go to a quantum gravity kind of setup where it is expected that a microscopic understanding of it will give you these states. And it turns out that it can be exactly done in the framework of string theory with very high precision. But the only drawback sort of is that it requires supersymmetry. So we have been able to do it for BPS black holes, so to say. But whenever this can be done, this is quite precise. So in string theory, when we talk about microstates and macrostates, these are the two different pictures. So macrostates are essentially the classical regime where you actually have a black hole, and then you talk about the black hole area and black hole entropy and stuff like that. So here the gravity is in that some sense switched on. And then you have the microscopic regime in which you do not have the gravity switched on. And then you are talking about d-branes and then strings fluctuating on these d-branes. And the idea is that if you basically control the coupling, then at the weak coupling where there is this d-brane picture and there is no gravity sort of, then when you go to the strong coupling, there is gravity, and this d-brane picture with string fluctuating on it will condensate and give you an effective picture in terms of black holes. So this is the picture that we always have in mind. So I'll not talk anything about the strong coupling part. This is the macroscopic part. I will talk here of the weak coupling side, which is the d-branes and so as I said, the goal will be to compare these two regimes, and we will mostly concentrate with extremal and stable black holes, and also we are going to concentrate on supersymmetry black holes, which are the BPS black holes, and then we can calculate certain quantity like Witten index or BPS index, which are protected on both sides of the microscopic and the macroscopic region, and then we can compare something. So turns out that these BPS black holes, modulo some complications of signs and etc., and soaking up of zero modes, etc., these BPS index of these black holes are essentially the black hole entropy. And the matching have been an important problem in string theory because string theory predicts both the macroscopic and the microscopic side. So for string theory to be consistent, both the macroscopic and microscopic picture should give the same results. And whenever we are able to do it, for example, in n equal to 4, n equal to 8, or partially for n equal to 2 theories, this microscopic and macroscopic result do match. So this is considered as one of the success stories of string theory, so to say. So our goal ultimately would be to say something about the microstate counting of n equal to 2 black holes. So in n equal to 2 black holes are black holes where you are doing the compactifications in the 6 dimensions as a Calabi-Yau. Now in Calabi-Yaus, there are no one cycles. So because there are no one cycles, then there cannot be a running momentum or a winding number associated with this cycle, one cycle. So all the charges for the black holes have to come from d-brane charges. So the idea would be to compute the Witten index of the theory living on the intersection of these d-branes. Turns out this intersection is zero dimensional in the sense that it only has time for us, so that we will basically get a supersymmetric quantum mechanics on the intersection of the d-branes. But we will of course not directly go and do the n equal to 2 theories. It is quite complicated. So first I will try to, and we have not done it. So what we have done essentially is to try it for 1/8 BPS black holes in n equal to 8 theory, where we actually know the answer for torus compactification. So we have this famous D1, D5, KK monopole P system, for which the full answer is known in terms of a Jacobi form, this theta square by eta to the power 6. This basically generates all the microstates counting for all possible charges. So we know the answer from the microscopic side. So but this of course is not a pure driven system. So what we are going to do is to do some T duality and S duality and go from this type 2b picture to the type 2a picture of pure d-branes, and then repeat the calculation for this pure d-brane picture and see whether it matches with the dual answers that we already know. Turns out that it does matches for the low-lying charges. So we have of course done it for the lowest charge. So these are all 4 charge BPS black holes. So the smallest charge will be like 1, 1, 1, 1 for each of the d-branes that we have, and or in the sense D1, D5, KK monopole P, which were we would want to look at it. So in those systems, of course, the result match, and also for the non-abelian cases, for the low-lying non-abelian cases, we have matched the results. So that part of the difficulty in going to larger non-abelian cases is just the computational capacity need to be scaled exponentially, which we of course do not have at this moment. Okay, and then if I basically am able to do this 1/8 BPS black holes, then we can learn our lessons from doing this and then try to apply this for, say, orbifolds of this compactified T6 torus that we have here, and then maybe calculate some other kind of twinings also for this. So once we have a full understanding of this 1/8 BPS black hole story, then we can basically slowly try to go to n equal to 4 and n equal to 2 ultimately. So n equal to 4 will be the K3, n equal to 2 will be some Calabi-Yau compactification. So the problem essentially boils down to computing this Witten index in an intersecting d-brane picture, and this effectively boils down to counting the number of solutions of some matrix equations subject to certain complexified gauge transformations. So we have like 4 d-branes, so there are 4 gauge groups, and then we have to complexify those even gauge groups. These are this GL N1C, GL N2C, and etc. Right, and then we have to and the coefficients of these matrices are basically just the expectation value of various fields that are there in the d-branes. And so this is what it ultimately boils down to. Now I will just flash one result or a conjecture that we propose, is that if you switch on generic points, or if you go to the generic point in moduli space, by this what we mean is that in the compactified T6, if you switch on background G mu nu and B mu nu fields, just to give it a moduli, then at a generic point in this moduli space, if you do the counting, you exactly get a collection of points for these microstates. And because this is a collection of points, they have to carry zero angular momentum. So all the microstates that we find are actually carrying zero angular momentum. So this is actually counting the number of microstate rather than an index. So in the usual, say, D1, D5 KK monopole P system, we actually calculate an index. The states that are contributing on that index have all kinds of angular momentum. They cancel each other, lot of cancellation, and then you ultimately get some finite number for a given charge. But this exactly getting the number of microstate that you need. So there is no cancellation of bosonic or fermionic degrees of freedom here, so or the states here. So this is all either bosonic or fermionic, whichever way you want to label it. Let's say I label it as bosonic. So all the states are bosonic here, and this number of states is actually the number of microstates. And this will have a interesting, maybe say I should say complications for the fuzzball program, because in the typical fuzzball programs, the solutions that you create, they carry angular momentum. So if you are basically saying that those microscopic solutions that you are creating in fuzzball program are actually the microstates of a black hole, then they should carry zero angular momentum, but that is not what usually happens in the fuzzball program. So if you try to, so maybe it can happen that if you try to repeat the fuzzball program in generic points in moduli space, which probably is super hard, you will basically have solutions which are zero angular momentum, but so far they are very rare. Zero angular momentum solutions in fuzzball are very rare. So let me come to the setup of the problem. So what we have is 4 D branes, and with 3 D2 branes with charge 1, 1, 1, and another D6 brane with charge n. 0, 1, 2, 3 are basically the non-compactified directions. So first D2 is compactified on 4, 5, the second on 6, 7, the third on 8, 9, and the D6 is compactified on the 4, 5, 6, 7, 8, 9. So this is all T6 compactification of a type 2A theory. Okay, so the microscopic description, this is the microscopic description for a 1/8 BPS black hole in n equal to 8 theory. For yeah, so if you make the charges large, it will be the of this black holes. So we have to calculate the weighted index for this D brane system, and we'll just concentrate on the low-lying minimum energy modes, which are basically the zero modes of the system. And as is seen from this picture, the only common direction for this intersecting D brane is time. So the theory that we will have is a supersymmetric quantum mechanics living on this intersection with some superpotentials that we have to figure out. Okay, so let's try to build the SUSY quantum mechanics that lives on this intersection. So the fields basically will be given by the open string spectrum in this brane background. So there will be strings that are connecting from the same brane to the same brane. There will be strings that are connecting from one brane to the other brane. So this basically creates a spectrum of fields, and we have to see what is the spectrum, which of course we calculated. And then you arrange this in terms of a SUSY multiplets, and supersymmetry almost dictates a lot of the interactions of this supersymmetric Lagrangian that we are going to write down. And then if you try to find out the Witten index, that will essentially be the Euler characteristics of the vacuum manifold of this supersymmetric quantum mechanics that lives on the intersection of the branes. So only complication, one complication, of course, is that we have a gauge theory here. So all this vacuum manifold, the characterization of this vacuum manifold has to be up to the gauge transformations. So the field content are as follows. In the same brane, we have this VI, PI, I is the index of the brane. So I basically is 1, 2, 3, 4. So for the 4 branes. So this VI, PI, QI, RI, so they are all in the adjoints of the Ni is basically the charge of the ith brane. So for the first for the first three branes, we have taken the charge to be 1, 1, 1 for the D2 branes, and for the D6, we have taken the charge to be n. And then there are these bifundamental or anti-bifundamental fields, which are basically strings going from ith brane to the jth brane, or the jth brane to the ith brane. So to give a physical interpretation of these fields, for the first brane, which is compactified along the 4, 5 direction, this V1 is basically just the 0, 1, 2, 3 coordinates. And this P1 is basically the Wilson lines on this 4, 5. And then Q1 and R1 is basically again, the coordinates 6, 7, and 8, 9. So similarly, you can give interpretation to all the fields in these other T branes also. So to gather some intuition, it is likely that the strings can, of course, see two branes at once. So there will be strings which is going from one brane to the other brane. So the Lagrangian can be built by a pair of piecewise interactions mostly. This is not true, but mostly the Lagrangian will be sum of pairwise interaction. And then with the mixed string that we have, this is the Z12, Z21, which are basically going from one brane to the other brane. They should definitely talk to the separation between the branes. So the separation between the branes are this V1 minus V2 and R1 minus R2. So they will talk only to the separation of the brane. The other sign, that is V1 plus V2 and R1 plus R2, these basically are the Goldstone modes of the system. So you have an intersecting D-brane system. So you can basically slide one brane past another. You can take the full system and slide it in some direction. So all those things are not really counting the microstates of black holes. So they are like overall motion. So those come under the Goldstone. And of course, we started with the 32 supercharges, and because we are dealing with 1/8 BPS black holes, we have broken 28 supersymmetries. So those will be the Goldsteins, and then there should be equivalent number of Goldstones, to just because you still have n equal to 1 SUSY left. So it should come as a super SUSY pair. So these Goldstones we are not going to look at, because they are overall motions. So we are only going to consider the relative counting in some sense. So the Lagrangian is the n equal to 4 super Yang-Mills Lagrangian for each D brane. And then there is the n equal to 2 Lagrangian, which is basically the Lagrangian for strings connecting from the one brane to the other brane. And then there are this Wn equal to 1. These superpotentials are also there, which is basically strings going from first brane to second brane to third brane, and then third brane to again coming back to the first brane. Okay, so these are the three different kinds of course, the n equal to 4 part has a natural superpotential, this P commutator QR. N equal to 2 has this Yukawa kind of superpotential. This Wn1 is something that we have to figure out, or we put it by hand. So I will basically say or try to motivate why this is the correct thing to do. But the other two are mostly fixed by the supersymmetry itself. So to coming to this Wn1 part, so one part is this root 2c and some signs and z. So this c is basically, as I said, this is coming from 3 string interactions. So this C can be actually computed by basically doing a 3 string amplitude in proper worldsheet open disk. So we have done that, and if you do that, it turns out that this C is basically plus minus 1. The signs can also be fixed exactly if you keep track of all the cocycle factors, etc., in this worldsheet calculation for the amplitudes, but we do not have to. It turns out that there are various discrete symmetries or exchange symmetries in this system, which are basically like you can take brain 1 and brain 2 and basically switch them. And then you can figure out how the Lagrangian should change and how the fields, some of the fields will pick up minus signs because of this, or other phases because of this, typically some eyes. So these kind of discrete symmetries are also there. So because they are there, you can actually fix all the signs here without really doing the full calculation for the 3-point Yukawa scattering kind of calculation. So this can be fixed. So the other part, the C12 513 minus 523 part of the superpotential, this is coming because you have switched on some background moduli fields in the T6 direction. So T6 are the compactified torus directions. So there we have switched on some B mu nu, G mu nu fields in the background, constants, but still we have switched on. So because you have switched on, the D-branes are not really perpendicular right now. So they have a tilt and angles and etc. So because of those, there are Fi parameters that need to be switched on. So for that, you need a term like this in the Susi quantum mechanics Lagrangian. And these terms are also necessary because these are the terms which make sure that all your Zs do not really vanish. So all the mixed strings do not vanish. That is, you basically get a bound state. If the mixed string, all the Zs vanish, then there is nothing binding the D-branes with each other, and they can really like travel or separate from each other as much as they like. We do not want that. So to bind these D-branes, you want non-vanishing mixed strings, the Z1, Zijs that we have. So for that, this is required that you switch on a term like this. So let me just quickly say about the abelian case. So in the abelian case, you have this 12 number of Zs, and then you also have these 3 complexified gauge symmetries. So there are 4 U1 charges for the 4 D-branes. One of the U1s is the relative U1, overall motion, so we do not count that. But then to basically figure out the supersymmetry ground state, you have to put all the D terms to 0 and all the F terms to 0 for this Lagrangian. Now it turns out that putting the D terms to 0 is equivalent to complexifying the gauge symmetries. So we complexify all the U1 gauge symmetries to their complex versions. So once you do that, the D terms are automatically satisfied. And then you are remaining with these 9 F term equations. And then if you solve it, you get this answer 12. And this, of course, matches with the answer that you get from this Jacobi form, from the D1, D5 KK monopole P system.
One question.
Yes.
By abelian, you mean there's only one brane of each case? Or?
Yeah, one brane of each. Yeah.
Okay.
So the charge is 1, 1, 1, 1.
I see. Thank you.
Yeah. So of course, the natural attempt here is to write everything in terms of gauge invariant objects, because we are dealing with a gauge theory, so we should be writing things in terms of gauge invariant objects and that is what we have basically done here. Like we have written this F term equation in terms of objects like Z12, Z21, which are basically the gauge invariant combinations. But it is difficult to do something like this for non-abelian cases. Because typically what happens is that in non-abelian cases, you have far too many generators for these gauge invariant objects than there actually are. So what happens is that you have many more generators for these gauge invariant objects, and to compensate for this overcounting, you also have a lot of constant relations among them. So I will show you an example, maybe in the next slide, which are called the syzygies. So because of this, we are really not aware how to actually do this kind of counting in a non-abelian setup. So how to basically figure out what are the minimal set or the generators of a non-abelian, in the non-abelian case, which will basically span the vacuum manifold. So the vacuum manifold has to be spanned by gauge invariant combinations of these fields. So what are the correct set that we are not able to find because of this issue of having a lot more generators and then compensating relations called CG So the one way to get around it will come to later, but uh, the way that we got around it is to basically by gauge fixing it. So you can actually gauge fix these solutions. And if you do that correctly, then we were able to solve this 1112 case, for which we got 56, 1113 case for which we got 208, and 1114 case for which we got 684. And all these numbers matches with the U-dual picture. And for this we have basically used this numeric computational algebraic geometry techniques. They are all numerical, this homotopy continuation monotony. And Hilbert series, though it is exact, can also be used here in the gauge fixing way. But as a theorist, it is not very satisfying to gauge fix something and count. So you always look for gauge invariant ways of doing things. So that can be done by in this method of Hilbert series, which I will come to in a while. Okay, but this Hilbert series method is computationally very hungry. So we are only able to do it for this abelian 1111 and the 1112 cases. But in principle, this can be done.
So sorry again.
Yeah.
Here you are changing one of the D2 brane charges, or?
Yeah, so in the non-abelian cases, let's say this 1112, this because it is 2, this is a non-abelian charge.
But
so
is it the
number of D-branes is 2 here, right?
Say that again, please.
So the number of D6 brane, so last charge is the D6 brane. So number of D6 brane is 2.
Okay, thank you. D6.
Yeah.
And if you change the other,
yeah, so order changing doesn't really matter much because we have these discrete symmetries. So yeah, so this order changing doesn't really matter.
Okay, thank you.
Yeah. Okay, so let me quickly build some basics. So there is this concept of a polynomial ring, which is basically if you have this coordinate x1 to xn, then all polynomials that you can basically construct. This forms a polynomial ring. And then if you have some special polynomials, let's say f1 to fk, then you can construct and then you can ask what sorts of polynomials you can create using this f1 to fk, and that forms this ideal. So if you basically put this f1 to fk to 0, that creates for you a affine variety, say vf. Right? So this is like putting hypersurfaces on a space. So that basically creates a affine variety for you. So that we usually call a coordinate ring. So the ring that will be formed by these polynomials living on this VF, which is the affine variety, is given basically by the original ring for all the polynomials, the C x1 to xn, modulo this ideal. Okay. And the generators of this coordinate ring, this RVF, we call the coordinates. Okay, so this RVF is called the coordinate ring, and the generators of this ring will be called the coordinates. Okay, so the main lesson here is that RVF, which is roughly a algebraic quantity, basically knows about the VF, which is basically the geometric quantity. So the strategy that we used for the abelian case is that we thought of these f-term equations that we have. We converted all those f-term equations to gauge invariant combinations, and we thought of them as this f1 to fk's as the ideals. Okay. So Then you basically take all the gauge invariant variables that you have, mod it out by these F term equations. You get this coordinate ring, which is this ring on invariants, and then the generators of this ring of invariants will be the coordinates. Okay, so because it was abelian case, it was relatively straightforward to do it, but this thing is not straightforward to do for the non-abelian cases. Okay, so let me give you a glimpse of the difficulty for the non-abelian case. So suppose you have this 3-node abelian quiver. So suppose you have this 3-node abelian quiver with bifundamentals. Okay, so even in the abelian case, you will be able to see the difficulty that you can face. So these fields that are there are the Z12, Z21, 1, 3, 3, 1, 2, 3, 3, 2. They transform under some gauge symmetries. Z12 is transforming like lambda 1 and lambda inverse, right? And the gauge invariant combinations are the Z12, Z21. Then the coordinates are basically this x1, x2, x3, x4, x5. These are all the gauge invariant combinations that you can create. But these are not independent of each other. There is a non-polynomial relation like this, x1, x2, x3 equal to x4, x5. So if you try to basically eliminate any of the coordinate from here, it would basically say if you want to write x1, then x1 would be equal to x4, x5 divided by x2, x3, which will be a non-polynomial relation. So you have CGGs like this, and even without any F term or any ideal to begin with, there is a ideal, and this is the CGG. The CGG is the ideal in this case. So the correct coordinate ring is this x1 to x5 modded by this extra constant that you have, the CGG. And this is just a simple case of abelian theories. The non-abelian things, you can understand that this will get much more complicated. So this is not a good way to go for non-abelian cases. You have to keep checking whether you have found new gauge invariant combinations or not, and whether you have a new gauge invariant combination, then you can also have a corresponding CGG to this, or you never know really where this list of gauge invariant operators will end or combinations will end. So you need a new strategy to deal with this. So the new strategy that we are going to do is this Hilbert series, where instead of basically thinking directly in terms of gauge invariant operator, we'll first create this polynomial ring R in terms of the basic variables, which are of course not gauge invariant. Then we impose the F term equation, which are again not gauge invariant, as an ideal on this ring and form this quotient ring R mod I. Once we have done this, we'll see that there is a way to extract the gauge invariant part from this quotient ring R mod I. And if you are able to do that, then that gauge invariant part will be the coordinate ring of the vacuum moduli space. And this is exactly what you need. To do that, we will use this idea of a Hilbert series. So what is this Hilbert series? So this Hilbert series is essentially nothing but a graded generator and a generating function for keeping some kind of grading. So for example, the simplest grading that you can have is that suppose you have this coordinate x1, x2, x3, x4, etc. You can say that the degree of this, I will keep this as a grading. So for example, x1 has degree 1, x1 square has degree 2. So I will basically attach a fugacity t to this degree, and then you can ask that whether I can create a series like ht, which is some hk t to the power k, where k is the degree, and hk is basically all the polynomials of degree k that you can form. Okay, so this spans a vector space. So this hk will basically be the dimension of the vector space vk, which is all polynomials of degree k. So similarly, I can generalize this degree idea to various other things, but this is the simplest example. So one such simplest case is this ring of, say, formed by this x1 and x2, which is, of course, a C square. And at level n, all the monomials that you can construct are x1 to the power n, x1 to the power n minus 1 into x2, and you can keep on going, and then x2 to the power n. So these are the things at level n. These are the independent things that comes in this vector space Vn, for example. Okay, so this will be the dimension k plus 1. So ht will be this summation, which gives you 1 divided by 1 minus t square. So this 2 in the 1 minus t square is basically telling you that this is a two-dimensional space to begin with. Okay. So in our problem, we definitely can have this degree, which will keep as a bookkeeping sort of charge. But then we actually have gauge symmetries, and we have all this field charge under the gauge symmetry. So we'll definitely have gauge charges, which are this Z gauge. So what we have to do is to generalize this graded ring to a multi-graded ring. So now you will have this T to the power M and also this Z to the power N. So there may be many Zs. So typically for us, we have 3 different U1 gauge symmetries. So there will be some Z1, Z2, Z2. So these are the fugacities of the, so the small Zs are the fugacities of the, which is keeping track of the charges of the gauge symmetries. And this way, this Hm, N is basically all the dimensions at some particular degree, M and N, or values. So this Hilbert series nicely have all the information. It turns out that once you are able to calculate this Hilbert series, you can extract the Z independent part out of this Hilbert series, and then the remaining Hilbert series in terms of the fugacities T will be the ring of invariance that you are looking for. And a further simplification happens if you sort of know from a priori that you are supposed to get collection of points that is a zero-dimensional variety. And in such cases, h of 1, if you put t equal to 1 in the expression for h, then that gives just the number of points. That is what the count is. So, for example, in this case of a toy example with only 2 fields Z12 and Z21, and a F-term equation like this, Z12, Z21 minus 1 and Z12, Z21 plus 1. Of course, if you solve this F-term equation, you have only 2 solutions, because this combination 1, 2, 2, 1 is a gauge invariant combination. So you have only 2 solutions in this vacuum moduli space. So if you want to do it in the Hilbert series way, you assign a U1 charge, which is the gauge charge U1, 1, 2. For Z1 to 1, Z21 is minus 1, and a bookkeeping charge, which is the degree charge, which is 1, 1 for both cases. Then the ideal F-term equation can be written like this, and you form a quotient ring R mod I. You can figure out, or there are ways or algorithms to compute the Hilbert series in such situation. It will basically come out to be 1 minus t to the power 4 divided by this 1 minus zt and 1 minus Z inverse t. So this denominator is definitely reminiscent of how you basically calculate bosonic oscillators. The same kind of computation is what is giving you the denominator. And the minus t to the power 4 is reminiscent of the fact that there is this ideal is a fourth degree ideal, right? So this is a fourth degree ideal, and this is coming as a constant. So therefore, there is a minus sign here. So once you take or extract the Z invariant part from this Hilbert series, you get the answer 1 plus t square, and the count again becomes 2, and which is the correct counting that we saw. So this you can now repeat for the abelian cases. I will not go into the detail as I'm running out of time. So you can get various Hilbert series. It is a complicated calculation. There is a huge numerator, relatively simple denominator. And then you have to extract basically the gauge invariant part. So the fugacities for the gauge are here T0, T1, and T2. So you have to basically get rid of this T0, T1, T2 from the expressions for the Hilbert series that you can do by doing a contour integral. And ultimately, for the abelian case, you will get the final result as HT3. And putting T3 equal to 1, you will again get 12. So which, of course, is the right answer. So this now can be also repeated for non-abelian charges. So for the non-abelian charges, you can take the Cartan of the non-abelian groups, and you can think of the charges in terms of the Cartans. And then the HTZ will naturally come as a character in the non-abelian gauge group, and then T to the power m, which was the bookkeeping charge. And you can basically then try to extract the gauge invariant part by using the Weyl integral formula or and the Haar measure and etc. So basically, you want to get rid of the z from here, so that you can do, and you will be left with a Hilbert series of only the fugacity T. And if you do it for the SU2 case, where the Haar measure is this and Z is the chemical potential for the SU2, you actually again get 56, which is the correct answer. So you can keep on doing this. Of course, we didn't do it because we do not have that much of computational power, but this method does work, and this is gauge invariant and so on. So from a theoretical physicist point of view, this is nice. But then there are these other strategies that maybe I will quickly cover, whatever time I have, which are numerical but still very efficient. So one such strategy is this homotopy continuation. So suppose you have a square system of k polynomials and k polynomials f1 to fk in k variables x1 to xk. So that typically a square system like this will give points at solution. So you will basically have certain collection of points as solutions. So if you have a square system like this, which is our case, for example, instead of directly trying to figure out how to solve this f1 to fk going to 0, you basically start with a much simpler system, the g of x, with some polynomials g1 to gk put to 0, which you can solve. The only constant is that you choose this g of k or g of x such that you a priori know that the number of solutions that you have from this g of x will be bigger or than the number of solutions you are going to have for the f of x. Then you can have a homotopy continuation map for some parameter t, like t into fx and 1 minus t into gx. So you can see that for t equal to 0, the gx is switched on. For t equal to 1, the fx is switched on. So in between, this is a mixture. So if I know the solutions for the g of x equal to 0, then I can start with that and then slowly vary the t from t equal to 0 to t equal to 1 to drag the solutions of the g of x equal to 0 to solutions of f of x equal to 0. Okay, so one easy choice of the system of equations that you can really solve is the total degree homotopy system. So you basically take something like x1 to the power some degree minus, so here these 8 a's and b's are all constant. So this system is very solvable. This is only one variable, some x1 to the power d. This thing we put to 0 is very solvable, right? So the total number of solutions here will be d1 into d2 into d3 up to dn. So just you have to make sure that this number, this product of all these degrees, are basically greater than the expected number of solutions for the system F that we actually want to solve. But as you can see, for our systems, because we have too many variables, for the abelian case, it's okay, but for the non-abelian cases, even for the small charges like 2, 3, etc., we have too many variables. So this number, d1 multiplying d2, dn, this becomes very large. So this becomes a very large number. So something like, say, 30 to the power 2. Or so, yeah, sorry, the opposite, 2 to the power 30, something like that, right? Was 30 being the number of variables. So if becomes numbers like this, then it becomes very difficult to track this solution. So you have to track this many number of solutions from G to F. So there are much nicer ways to do it. These are the recent developments in the couple of years. And these are to basically construct what is known as polyhedral homotopy. So this replaces this total degree homotopy, which looks nice and easy, with a much more efficient choice of GX, which uses something called Newton polytope for the target system f of x, and then convert that to a toric variety, and then various other simplification, modification, etc. Let me not go into those details, but a much more efficient system can be constructed such that the number of paths to be tracked is much less. And this is the system that we have used. So the tracking can be done by noticing that if g of x has a solution, then for in between t, we can parameterize solutions by x of t, and we can look for solutions of this h of x of t and t equal to 0. So this converts everything to a initial value problem. So we have an initial value, which is x of 0 is x naught. We have the initial value, and then you are going to change this 0 and drag it to t. This is the t, so you will drag it to 1 ultimately. So this gives you a first order differential equation, which is the Davydenko differential equation, by which you can track it. So the solutions of g of x equal to 0 can be tracked to solutions of f of x equal to 0. And typically what will happen is that g of x will have many more solutions than f of x. And many of those solutions will get tracked and basically diverge to infinity. So you discard all those solutions. So the whatever solutions, finite solutions that remain are essentially the solutions for the f of x equal to 0. So for our system, our system doesn't automatically come as a square sparse system, but after gauge fixing and using the shift symmetries and etc., you can make it a sparse system that is a square system. And there are other some simplifications that can be done. But what we have used from the algorithmic side is this new programming language called Julia, and a package called homotopy continuation that is written maybe 2-3 years back. And I also did some own modifications to it to adapt to our cases. But with this, you can now basically solve these cases for abelian and the non-abelian charges. So to just give you a flavor of the number of variables and the number of solutions. So you have 15 variables and 15 equations, and you have 16 paths to track for the abelian case, and you only get 12 solutions as expected. Then for the 112 case, the first non-abelian charge, you basically have 24 variables and 24 equations, and then 297 paths, and then out of which only 56 are finite when tracked. So you can see that as you go higher on the charges, the number of paths that need to be tracked exponentially increases. For even from just 2 to 4, it is like 297 to 2.5 lakh. So lakh is like 10 to the power 5. Okay. So this is the exponentially increase. So of course, computationally, this doesn't look too much viable, but the point is that this is also very fast. So if you try to do these cases, for example, a couple of years back, when we actually did the calculation, we tried this 1113 case in Mathematica. So that took, for example, about 10 hours, 6-7 years back. Now, if I now run it, it will take about 5 hours. So Mathematica essentially uses something called a numerical Grobner basis decomposition and other things, and it is not at all parallelizable. So if you do that, it will take 5 hours now, but this only took 1 minute. Okay, and it is not that we have too many cores or anything. We have modest number of cores, but so it is computationally very, very fast, much faster than anything available right now. So this is one USP of basically using this kind of techniques. And these are all parallelizable, completely parallelizable. So if you scale your computational system, you can do much more things. So for example, we have gone up to, I think, 5, 6 in the charges. So there are other techniques. So maybe I will just hint upon this. So there is something called a monotopic group action technique, which roughly says that if you have this solution F1 to Fk to solve, you basically just deform it by some constant parameters P1 to Pk. Okay, and then you can, if you start with one solution for this Fx comma P system, which you can always find, because for any choice of X, I can always tune my P's such that this is a solution for this Fxp. Then once I get a solution for some P naught, then I can go and make loops in the parameter space. So if I make loops in the parameter space, when you close and come back to the same P naught after a loop in the parameter space, you do not come back to the same solution that you had for the x's. So if you started with x naught P naught, you will basically end up with another solution, some x tilde naught P naught, if you make a loop. So by making such loops, you can find out all the solutions for this system for a given P naught. Okay, and then you can again do a homotopy continuation to track this P naught from some finite P naught to zeros, because what we actually want to solve is all these F's, F1 to Fk is equal to 0. So this also can be done, and turns out that this is even faster than the previous technique. So this is about 10 to the power 10 times faster than the homotopy continuation itself. So I will not probably touch upon this Newton-Pareto because this really does not work except for the abelian cases. So this is not general. But this is useful to know because the polyhedral homotopy, this construction of this G of X requires knowing the Newton-Pareto, etc. So I will directly jump to the outlook. So what we have discussed here is a de-Bruijn system where you have switched on certain background moduli fields, and this is this intersecting de-Bruijn system is counting the microstates for a 4-charge black hole. And turns out that this counting is exact counting in the sense, as I mentioned earlier, these points have only 0 angular momentum attached to it. So the number of points you are getting is exactly the number of microstate that the black hole should have. So there is no cancellation of bosonic or fermionic happening here. This is exactly the microstates that you are supposed to get. So that is one nice thing about switching on background moduli field, that you basically get what you exactly want, rather than really an index calculation where a lot of different angular momentum states will cancel each other and give you the right answer. Okay, so but to do that, you have to, of course, do the computation in a generic point in the moduli space, which in most situations is very difficult to do. It turns out that for our situation, it was reasonably okay to do, but as you can see that if you turn on these generic points, the computation is at least conceptually it is clear what to do now, but computationally at least actually to solve these things and put it in computer and solving it becomes very challenging now. So this computing things at generic points in moduli space is challenging. So that's why all the original calculation, for example, the original D1, D5, KK monopole P computation, etc., are all done in very special points in moduli space where most of the moduli is put to zero. And if you put most of the moduli to zero, you naturally get all kinds of angular momentums which have to cancel each other ultimately. So we can go for the 1-1-1 cases a higher, but more interesting things happen if I now go for 1-1-N1, N2. So if I switch on two abelian charges, so for example, 1-1-2-2 or 1-1-2-3. So here somehow things are not working out as expected. And it is not working out in a very precise way, in the sense that for example, the calculation of 1-1-2-3, from the dual system, the count that I should get is 5-6-1-6. And what we are getting is 3-5-8-4, which is strangely 5-6-1-6 minus 2-0-3-2, which is the counts for the 1-1-1-6 and 1-1-1-5 respectively. So so either we are missing something here, or something was missed in the original computation. So whatever be the case, this is something that we are trying to resolve right now. That what happens if I switch on, say, two non-abelian charges instead of one. Things also have to be matched. So as I was in the number theory program in Trieste this year, we discussed a lot about whether this falls under some sort of extended Langland programs or not, in the sense that you basically have a set of polynomial equations which is giving you a variety, and this we know are related to coefficients of some Jacobi form. So in some broader sense, this must maybe also thought of as some kind of Langland program, but we don't know what to do with this. But then if we manage to make things more precise for the other non-abelian charges, then we can move to the n equal to 4 and n equal to 2 black holes, which are basically the orbifolding of this T6 space in some way. So, okay, so with this, I will probably end. So thank you for listening.
Thanks very much, Abhishek. Thanks.